Hello everyone, this is AI Critic. Last couple of videos we were pretty heavy on AI, so let's take a step back a bit and let's talk about predictions. Because predictions are important for AI neural networks, as I've said in my striking AI video. Now, why are we talking about uh, all of this? I have actually produced a program um, on doing these predictions a few years ago. So, what we're going to talk about in this video is number prediction, and I am going to show you a program that is able to predict almost any pattern you put into it. So, let's get started. Do you remember when you were studying quadratic sequences in school? In school, so the point here is that what you did essentially was find the first differences and the second differences and sort of look for them to be the same. Now, it just so happens that the same is true for cubic sequences. As you can see, the very same thing is happening here. So we've got a sequence here, and as you take the first differences, the second differences, and the third differences. Now, I know what you're thinking here. What if this works for more sorts of sequences? Well, it just so happens that in 2018, Professor Dave Richson actually proved this fact. So thank you to Dave. Um, so he proved this, that it works, that you can increase the degree of the polynomial and just go on extra lines of differences, as follows. So this is quite useful, and it's going to be key to the program that I am going to show you. Now, my program needs to not only do these polynomials, but also I had a look at geometric sequences. So, if we remember that geometric sequences are essentially just a sequence of numbers multiplied by the same common factor, then we already see a similarity. We already see a similarity to here. So we've reached a line where all of these are similar. And so in geometric sequences, all the terms are multiplied by a common ratio. So there's this common thing in this sequence that I can exploit. Let's have a look at the program. So essentially what I'm doing here is using a recursive algorithm to cycle through and and find the differences and the division differences to find those geometric sequences. Um, I'll talk more about how that code works a little bit later. Let's run this. Okay. Right. So now we need some good sequences to test. Um, let's start with the obvious one. So 1, 2. Okay, see, it's already predicted 3, and it's gonna keep predicting the same other ones. Next, let's have a look at a quadratic sequence. Let's have a look at triangular numbers. So, triangular numbers look like this. Essentially, we're putting dots and arranging them into a triangle and just adding layer and layer and layer and layer. And this sort of pattern emerges. It just so happens that this pattern is a quadratic sequence. So, let us test this out. Let us test this out. So I'm going to start with 1, 3, 6, and 10. That is correct. So 10, 15. So it's solved. It's solved and predicted this pattern of triangular numbers quite quickly. Let's have a look at a geometric sequence. So geometric sequences are quite easy. They've only got a simple multiple in them, so I don't need to look at them much more than I am doing now. 2, 4, 8, 16. So what I'm doing here is powers of 2, which my program has found actually quite quickly. This is probably not that surprising. It's not that difficult. So let us have a look at an even more complicated pattern. Let's have a look at a pattern that's similar to that, and let's try to confuse the program. So, this is Moser's circle problem that's spelt over there. We are basically taking a circle. We're putting points on the circle, and we're joining them up. We're joining them up. We're joining each point to each point, and we're looking at the number of divisions of the circle that are left. And it just so happens that this is a quartic sequence, which is quite astonishing. It starts with 1, 2, 4, 8, and then it goes 16, 31. Imagine that. So at first we thought that this is just, again, 2 to the power of a number, but it turns out that that is not the case. Now, if you want if you want to understand why this happens, if you want to check it, honestly, just take a circle, put some points around it, and join them all up, and then count the number of sectors of the circle that are left. It will take a while to get that 31, but if it's worth your time, then why not? But I'm not going to do that. Definitely not worth my time. So then, we have this pattern. Let us put it into the program. Let us have a look. So how did it start? 2, 4, 8, 16, 31. Okay, and the program has immediately picked up the next number in this Moser circle problem, which is quite astonishing. The next one is 57. Does it predict the one after that? Yes, it does. 99 and 163. So you get it. My program works for those sorts of patterns. Now, let's have a look at the code one more time, and let's try to make a conclusion. So the way my program works, it's recursive, and it looks at the differences. It tries to see if they are the same, if any of them are the same, until the list of differences is only one item. Okay? And my program also does the same for the divisions between the numbers. It looks for the exact same thing and keeps going until there is only one item in that list of multiplications, of divisions. Now, what is interesting about this code is that we can look for complex patterns that we can't even imagine, because we can look at the differences and then we can look at the divisions on the next step, and then back to the differences. This will sort of mean that we can look for lots of complex patterns. So I was thinking that it could perhaps solve some more complex patterns. So let's have a look how that worked out for me. So the next one we're going to use is the Fibonacci sequence. Now this is going to be very different from any of the other sequences that I've used. It's going to really put the program to the test if it manages to solve it. So the way the Fibonacci sequence works is by adding the two previous numbers before the next number. So as you can see, we've got 1, 1, and then 2, that's 1 plus 1, 3, that's 2 plus 1, 5, 3 plus 2, and so on. So this is a more complex pattern. So let's see how the program works for this sort of pattern. So that's 1, 1. Hmm. Seems it's crashed. Give me a minute. Okay. 1, 1, 2, 3, 5, 8. And then what's next? It's 8 plus 5, that's 13. And then 21. And then 34. Now, I'll give you the answer. In short, the program is never gonna actually solve this. So perhaps I do need a more complex program to do this. I made the program a few years ago. I'm not entirely sure about some of the aspects of it, although um, although I know enough to talk about it. So we've shown that the Fibonacci sequence doesn't work as a last try. Let's try something that no one has found the pattern of, something that we're not going to find the pattern of. Let's just test that and see what happens with the program. So we're going to try prime numbers. If you don't know what prime numbers are numbers that cannot be divided by other integers to give an integer result, other than 1 and itself. So they start 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. Okay, so what you see here is that the program is just going bonkers. It's going up and down. Why is it going up and down? It's because of the differences inside of the divisions. They allow for negatives. They allow for the numbers to get smaller, and also to get bigger again, because if there is a multiple of -1 inside the multiples, they will obviously fluctuate up and down. So I hope that is quite interesting. Let's have a further look at the code. I'll just say a few points and then we can wrap up. So I've split this into the recursive function I've told you, and this list, the sublist, is the subtractions, and the multi list is the sort of divisions between them. And as you can see, it will add those sorts of things inside those lists, and also and also the recursive part starts here. I've made the subtractions get recursive before the multiplications to give them priority, because as humans we tend to put those sorts of sequences before geometric sequences. It's just sort of polynomial sequences just feel simpler. And so for this, as I said, this means that we can have really complicated sequences that I can't show you because I can't even imagine it. It's like there is a difference. There are differences between the numbers, and there's also divisions between the differences, and divisions between the and differences between the divisions of the differences. That sort of thing, and something in that area will be the same. Those sorts of sequences are going to be quite interesting. But as I've shown you, this program doesn't work for everything, and also I will drop all of the code, all of the files that I have used, everything in the chats in the video. So make sure to like and subscribe.